Hello, so are there any questions? I will look into chat. No questions voiced, no questions in the chat. So we will continue now with the question how to solve the Sato-Tifka equation. Just, you see we have quite a simple geometry. Let's say you make 20 cuts in one dimension and 20 cuts in the other dimension. Well, there is some amount of missing points here, but anyway, let's say 20 by 20 is 400. So normally, with a brute force, we would get 400 equations. And to store that, we would have ordinarily have a matrix of 400 by 4 columns by 400 rows. That would be quite a bit matrix, just if you use that. 400 by 400 is something like 16,000. And now 16,000 times 10 bytes per variable would be, let's say, close to megabyte. Not very much memory today. Just those calculations have been started with 8-bit computers with 16 kilobytes of memory. The second point, if we were not able to get enough precision, we would have to make a bit more points. So if you cut it into, let's say, 1000 by 1000 points, it's still not much. You will get 1 million points inside, and matrix 1 million by 1 million would be rather big even for today's computers. But in fact, how the matrix would look like? Well, first, it would be full of zeros. There would be only 4 non-zero elements in each row, because the point here generates contributions for its 4 neighbors. So it's wasting of memory to store the matrix this way. The second point is we have to forget about inverting the matrix. So we would have to find an iterative way how to proceed from an initial guess to a solution of the matrix equation. And this could be done in the way that we only store each point once. So we, instead of storing a matrix of the equation, we just store a matrix containing the points, containing the potentials of those points. With a more or less a rectangular area, we can store that in a square matrix. Now that's the first point. The second point is that we might now have some important considerations at the beginning. First, mathematicians do support us with several important rules or laws. First, we can start the calculation in an iterative way from any guess. So if we guess a very bad guess of the field, like if the boundary conditions like here is 1 and 0, and we somehow guess that the points inside would have 1 million as a potential. It's a bad guess because all the points must be between 1 and 0, but it's a bad guess. Anyway, if we start to apply an iterative method, I will describe later, it will converge, just it will take some more time. So that's the first point. The second point is a method that is called successive relaxation or relaxation. Now, why relaxation? Just imagine a mathematician who is sitting here and has no computer. He has just a big wall with, or big table, where he has written all those potentials. So a little bit bigger paper, and he has written all those potentials to the points. And a mathematician must feel a big discomfort if he just looks on that and says, okay, but the point over there does not fulfill the condition. This is not the average of those points around. So in order to relax his stress, he would change the value for that ugly point. So he would substitute the value here by the average of the points around. Unfortunately, that would mean that he would feel stress in another point. Now, with a mathematician, with a very powerful brain, that would be the most easy or most fast solution, is to correct those deviations from the average just in the points that are most violating the condition. So he would write a big wall of numbers, just look and say, oh, there is, repair it, where is it, repair it. And by this relaxation of his stress, he would create a most effective way how to get to the solution. Unfortunately, this is not a very good method for a computer. While a mathematician just looks on the numbers and say, hey, 0.75 is delinquent, a computer needs to find out the deviations in all points in order to find out that point which is worst. But to find the deviation, he or the computer must calculate the averages. So finding the point with biggest deviation is as much computer cost as correcting all the points with getting their new averages. So a computer method would do or would behave a little bit different from the mathematician. We would just set up the boundary conditions, set up the metrics, and have some estimate. For example, we have 1 and 0 as boundary conditions, so let's give to all the points inside at the beginning 1/2 as an estimation. And then the computer would scan line by line or column by column the whole area, and at each point it would substitute the value by the average of those 4 neighbors. Just to do that, we need 1, 2, 3 additions and 1 division by 4. And that's it. We would scan the matrix. Unfortunately, just imagine the situation. For example, we have several points. We have boundary condition of 0 on this wall, boundary condition of 1 on this wall. And we have several points here, 1, 2, 3, 1, 2, 3. Just now, imagine that we gave 0 to all the points inside at the beginning. So in the first step, we will get to this point, and we have 0, 0, 0, 1 as his neighbors. So we would put here 1/4. The next elaborated is this point. This point has 1, 0, 0, but here we already have 1/4. So this point would be bigger than this one. And after we do the whole scan, we return to the first point for second iteration. Surprisingly, the average here is no more valid because those points have changed. And second point, as you can see, we will first increase the value in this point. And in the second iteration, we will again increase it because the surrounding points have increased their potential. So, in fact, the iteration would be increasing and increasing and increasing the value. Just in order to speed it up, there is something which is called super relaxation, so or successive over relaxation. Now let's get back. With an iterative procedure, we start iterating, so we will do one sweep of the matrix, substituting averages instead of the values, then the second sweep, and we'll sweep so long, or as long, as we will find out that the values are not changing anymore, or they are changing only very, very little. Now this would need a number of iterations. Just imagine that you have, for example, this arrangement. You start and you sweep this way. So in fact, the information about this wall or this boundary condition gets only one row up in each iteration. It propagates quite well in this direction because you sweep this way like a TV set, but in this direction it's not as fast. So you can imagine that the number of iterations would be quite substantial, and that would take some time. Now let us continue with a better method, which not only puts there the average, but an overestimation. We would have to work it into equations a little bit. So again, we have still those 4 points. Now we have phi 1 plus phi 2 plus phi 3 plus phi 4 divided by 4, which is the average. Now, in the first method, relaxation, we would put the average just directly here. At this point, we would make something a little bit different. We will find out the correction, that is, how much should be added to the central point to get it to the average of its neighbors. Let's calculate the correction. The correction is the average minus the actual value. So the correction C is the average minus phi 0. If we add correction to phi 0, we would get the average. And the trick with over relaxation is that we not just add the correction, but add a little bit more. So instead of putting average into phi 0, we do put there phi 0 plus not only the correction, but a correction multiplied by a coefficient alpha, which is called an over-relaxation coefficient. Over-relaxation. Okay, so we have this coefficient. Now, what is a good choice of that coefficient? First, we can easily see two important values. If alpha is equivalent to 1, we have the old relaxation method, because we exactly put to the phi 0 the average of phi 1, 2, 3, and 4. So alpha equivalent to 1 is not very interesting. Now if alpha would be 0, we would have a never-ending story of never-ending computation, because nothing would change. But there is another problem. If we raise alpha to 2 or more, we get a serious problem. I will show you why in 1D. Let's say we have 3 points, of which those 2 are fixed to 0, that's the boundary condition, and we have one 3 point in the middle with starting potential of 1. Now, if the over-relaxation coefficient would be, for example, 3, then the average is 0, the correction is -1, the over-relaxation coefficient is 3, so that we should put here -2 as a second value. Now, another step, we have still the average of 0. With the over-relaxation, we put here +4. And as you can see, the solution would diverge in each step, increasing its absolute value 2 times. So, what is important, we cannot increase alpha over the value of 2. Now, there is a question which is important. Is there any optimum value of alpha that would maximum cut the number of iterations needed to get some precision? And yes, there is a solution to that. Mathematicians do have a method that can give us an optimum coefficient of alpha for solving a set of equations in this way. Well, there is one slight problem. It is numerically more demanding than solving the equations by the simple method itself. So yes, we can find the optimum at a cost that is more costly than using alpha equivalent to 1. But fortunately, at least for rectangular areas, I mean areas that are more or less looking like a brick or a rectangle in 2D, there is known the behavior of the optimum coefficient. So if we plot the coefficient alpha and the number of iterations necessary to reach precision, we would have, well, for alpha of 0, we get to an unlimited number of iterations. Then for alpha equivalent to 2, we get to divergence. So 0, neither 2 is a valid option. And in between that, the function behaves something like this, where the optimum is close to 1.4. It depends on the shape of the region, so, and the boundary conditions. So take that like a rule of thumb. But anyway, it's close to 1.4. And the general knowledge tells us that it is better to overestimate the coefficient a little bit than to underestimate it, because this part is less steep. So this is steeper. So it's better, if you do not know the optimum coefficients, it's better to overestimate it a little bit. The choice mostly is that we take alpha equivalent to 1.5, 1.5. And the second question is whether this pays off. And yes, we can beat the number of iterations dramatically. I mean, by several orders. That is, we can save a lot of computer time. Well, okay, now we have a method that can solve the Laplace equation in order to find out potential in 2D or 3D. Just short remark, the derivation of a 3D method would be quite similar, just we would have to divide by 6 to get the average. That's the only difference. So now it seems that we have tools to find out solutions to simple problems using the finite difference method, and that is what we can do now using a computer. Now, as to implementation, that's a very important point. You can do this in Microsoft Excel. With a rectangular area, it's quite simple to get it with the Excel. Excel is able to provide iterative approaches, just you have to set manually the number of iterations it does. It's quite easy to do that in Excel. It's very slow, but it works. So I think that I have already supplied an Excel file to the Moodle, which works so that you have the first row and column as boundary conditions. You can change it, and then it calculates the interior points, and let's say by several colors of the background using condition formatting, it draws you something like equipotentials in the thing. You can play with it. Excel is not a real tool for mathematics, but anyway, it works somehow. The second point are now considerations about the speed of programming or speed of calculation. You can do this as a brute force easily. I mean, you just program it, and programming this algorithm is something that is running on 10 lines, I think, including saving the result to a disk. But anyway, if you think a little bit, it may save you a lot of time. Now, I would like to make a small competition. In order to do that, we have to set up a problem